Hope you can hear me. It's a pleasure to welcome you all to this Feindel Virtual Brain and Mind seminar. And just before I introduce our speaker, let me remind everyone who's joining us to just mute your microphones so that we don't get dogs barking or babies crying in the background. And also, if you have questions, which we hope you will, please hold them until the end. And when you're ready to ask them, you can enter them into the chat box, and then I will be happy to read them out loud and ask our speaker to address them. So let me just introduce today's speaker, who is Mor Regev. Mor has, well, she started off with her bachelor's degree in her home country of Israel, where she studied psychobiology at the Hebrew University of Jerusalem. And there she worked with Amir Ahmedi, some of you may know him, and she was interested in body rotation and sense of embodiment. And then after that, she did, after a short stint as a research assistant at NYU, she did her PhD with Uri Hassan, who many of you will certainly know if you do brain imaging. And that was at Princeton University. And there she did some very interesting work on the processing of auditory and visual linguistic information and the way in which those networks are linked. And that's really where she learned to do the technique that she'll be talking about today, which is this intersubject correlation technique, which was developed partly by Hassan. She is currently a postdoctoral fellow in my lab at the MNI. And during the first couple of years of her time here, she obtained a fellowship, a postdoc fellowship from the Tannenbaum Foundation. And in fact, it was went through the Israeli program in brain, mind, and consciousness, which is part of the Canadian Institute for Advanced Research. So that is how we brought Mor to Montreal. And since then, she's been doing some really great work on looking at the application of these techniques of intersubject correlation to a very complex and interesting problem, which is the internal representation of auditory information. And we call that auditory imagery. And I will let Mor tell you about the cool stuff that she's been doing. So please take it away, Mor.
Thanks for the introduction, Robert, and for inviting me to speak in this virtual seminar. I'm delighted to be here. Today, as mentioned, I'll present my recent work on auditory imagery, which is quite a common experience in our daily lives. For example, whenever you imagine the happy birthday song, hopefully it happened quite often recently when you're washing your hands very carefully. So when you're doing this, you're likely to experience some auditory features of the melody or of the lyrics in your mind without actually perceiving any auditory input. And today I will be focusing on music, which is one of the most complex auditory content people can imagine, often containing many auditory components that evolve over time, creating an engaging experience that resembles to some extent the experience when listening to music. So it's not surprising that studies showed a similar set of cortical regions that are active in both perception and imagery of music, including mostly secondary and associative auditory cortices, as well as other frontal and parietal structures, such as the supplementary motor areas. However, most of these neuroimaging studies only identify a basic cortical overlap in the signal across perception and imagery, and therefore they could not detect potential differences across these two states in the neural processes that might take place in a region. So for example, they cannot identify whether a region might contain information about a specific melody in mind, or be involved in a more global process that is not unique to the musical content. So in this study, we asked to what extent do neural responses during imagery of musical sequences resemble the responses during perception. And we wanted to know not just which regions are active in both perception and imagery, but whether they function in the same way across these two forms of musical experience. And more specifically, we ask whether such a region might represent the specific musical content similarly across perception and imagery, or otherwise has a more general involvement in these processes that is more invariant to the specific auditory content. And finally, we know that the auditory system does not work in isolation when complex sounds are perceived. The neural representation of sounds was shown to be modulated by movement, such as enhancement of perceived sound by rhythmic tapping, as demonstrated nicely by Sylvain Bayet groups here in the MNI. So therefore, we also asked whether movement could also modulate the representation of music during imagery. So in our experiment, each of the participants started the experiment by memorizing 6 melodies, each about a minute long, taken from soundtracks of animated movies. And these instrumental melodies were matched to each other for their timing of their beat and had no lyrics. And here's, I'm gonna play the beginning of one of the melodies, for example. Okay, so participants learned independently at home to hum each melody very accurately, accompanied by a visual metronome in the form of a bouncing ball to guide their tempo. And only participants who successfully learned to hum all the melodies took part in the fMRI scan. And in the scanner, for each melody, each participant first listened to the melody with an empty screen, then imagined the melody in silence twice, once with and once without finger tapping to the rhythm of that bouncing ball. We also had a control condition in which participants view the ball without the musical imagery task. So instead of the traditional task versus baseline comparison of the average level of bold, we used intersubject correlation analysis to compare the temporal patterns of the signal. So in this method, in each region, we correlate the full minute-long time course between different subjects while they, for example, imagine the same melody. So this correlation value provides us a measurement of how reliable the signal is across people within that region when they imagine the melody. So when we see a reliable response across people, it means that this temporal alignment must come from an experience shared by them that synchronized their brain activity, which in this case would be the imagery of the melody. When there's no shared experience, for example, in a typical resting state, there's no reliable response across subjects. So correlations were threshold using a bootstrap analysis where the phase of is scrambled before performing the correlation. And using this intersubject correlation analysis, this method, we began by establishing to what extent and where in the brain imagining the same elicited a synchronized neural response across people. We performed the analysis within 400 parcels of the entire cortex by Scheifer et al., which were independently defined based on resting state. We found reliable temporal responses across participants at the center of the dorsal parts of the superior temporal gyrus bilaterally, which largely overlap with Heschel gyrus, as well as in associative auditory regions in more anterior and posterior dorsal areas of the gyrus, and also in lateral parts of the right STG. For comparison, we performed the same analysis for the control condition when subject viewed the same metronome without performing the imagery task, and no reliable response was observed in the control condition. So this means that the common task of imagery was the factor that evoked the similar temporal patterns across people in early and associative auditory cortices. But what does this similarity of response represent? The shared experience of imagery has many components, so the neural similarity might have been evoked by common replay of the perceptual experience of music, but it could also be a result of shared responses that are idiosyncratic to imagery and are not represented during perception. So to identify regions with shared neural representation across perception and imagery, we turn to compare the temporal patterns not just between people, but also across perception and imagery conditions. And this allows us to identify regions that respond similarly when imagining a melody and when listening to it. And therefore, this correlation represents the shared representation of the melody reinstated during imagery. These comparisons revealed that only a subset of the regions that were involved in imagery have a similar response as during perception, including bilateral early auditory regions and associative auditory regions, mostly in the right STG. We have 5 parcels here overall. But this consistent response across imagery and perception could still be related to either general cognitive trends common to both tasks, or could represent the reinstatement of the specific musical content with temporal patterns that are unique to the experience of each melody. So to test for the specificity of these reinstated responses, we used the permutation analysis that compared temporal pattern similarity between matching melodies against the random sampled non-matching melodies across perception and imagery. We can say that neural responses to the specific musical content is reinstated if the similarity of the matching melodies is greater than the similarity between the non-matching melodies. This analysis was performed within the 5 parcels found earlier and revealed that the right associative regions in the center and somewhat posterior part of the lateral STG are showing greater within versus between melody similarities. We also performed a classification accuracy analysis for these 2 parcels in the right lateral STG. And in this analysis, participants were randomly split into 2 subgroups, and the average temporal pattern was compared across these 2 groups in all melody combinations. The classification accuracy was calculated as the proportion of melodies correctly identified out of the 6. And the procedure was repeated using 200 random group combinations, as you can see here in the plot to the right, all the yellow marks, and then average, which is the black bar. The classification accuracy was found to be significant in both of the parcels in this right lateral STG. So together, these results suggest that the associative auditory regions in the right STG contain melody-specific patterns that are reinstated from perception during imagery. It's also interesting to note that these two regions in the right lateral STG also showed the strongest relationship between the levels of neural reinstatement and levels of accuracy of imagery. I haven't mentioned yet that before the scan, we tested participants' accuracy in imagining the melodies in time, whether they can keep the rhythm of the presented metronome without skipping a beat while imagining the melodies. We can see in the two regions here a correlation between this behavioral measurement of accuracy and the strength of the replay of the neural patterns, which is on the y-axis. So admittedly, this is not a strong effect, but I still find it interesting that out of all the cortical parcels, these two are the ones to show the strongest indication that the reinstatement of the neural response during imagery can predict the accuracy of the internal musical experience. Okay, so now that we found a melody-specific neural representation during imagery, we turn to explore whether it might be modified when the imagery is accompanied by rhythmic tapping. For this purpose, we repeated the intersubject analysis, but now between perception and the imagery condition that included tapping. You might notice that in this case, there are overall more areas in the auditory cortex that showed similar response across perception and imagery compared to the imagery without tapping shown earlier. And within these now 9 parcels in the STG, we also repeated the same discriminability analysis, which now revealed that tapping extended the melody-specific response to further associative areas in the dorsal STG bilaterally, in addition to the right lateral ones identified before, but not to early auditory cortex, notably. Previous studies suggest that these dorsal areas might differ from the lateral ones in their involvement in integration and recognition of relatively more fine-grained auditory patterns. And finally, now that we observed the additional inclusion of more dorsal regions of the STG, we asked what functional connectivity might support that spread of melody-specific information during imagery with tapping. To map how melody-locked responses are shared across brain regions, we used intersubject comparisons across different brain regions. And in this analysis, we correlated the temporal response across people and across conditions, but also across brain regions. So instead of the familiar functional connectivity analysis performed between regions within the brain of the participants, this version of the analysis is performed across different brains. And that allow us to filter out intrinsic neurocorrelation and other confounds, leaving us with the ability to detect interregional coupling that is induced by the recalled musical experience specifically. So we performed this analysis twice, between perception and imagery without, and perception and imagery with tapping. And then looked for the difference in connectivity due to the added tapping component during imagery by doing a simple subtraction of the two connectivity matrices. Here you can see the results of this subtraction within 17 functional networks in which the 400 parcels of the entire cortex were organized. So in the connectivity matrix here, which is practically a triangle, the brightest the pink is, the strongest the enhancement due to tapping in the shared musical content during imagery. You can see that the strongest increase in coupling at the network level is observed within the ventral somatomotor network, here it's the fourth from the top, as well as between this network and other functional network, especially with the dorsal somatomotor and temporal parietal network, which are adjacent in the matrix, just above and below. And this is not surprising, considering that this ventral somatomotor network contain, among others, those dorsal auditory parcels of the STG, to which we saw earlier that the tapping extended the melody-specific response. When we zoom in on these three networks, we can see in more detail that tapping increased the spread of information between these dorsal STG parcels, as well as between them and other lateral auditory regions in the temporal parietal network and with different somatomotor regions. So to conclude, in this study, we were able to trace the neural responses associated with familiar musical segments and show the common ability to reactivate them at will when bringing to mind musical content. And our results show that the temporal response pattern that were shared across people during perception of music were reactivated in a melody-specific manner during imagery in associative auditory regions in the lateral part of the right STG. And this lateralization is in agreement with previous evidence that support the idea that melodic information is better represented in auditory areas within the right hemisphere. In addition, when imagery was accompanied by tapping, the distinctive responses to the melodies were reinstated and spread across additional bilateral associative auditory regions in the dorsal STG, making the overall neural activation during imagery more similar to perception. These findings suggest a common neural activation that is involved in creating both perceptual and imagined experience in regions where encoded information is largely sensory. They also demonstrate that the similarity in the neural codes is not limited to isolated neural population, but could also be observed in comparable interactions between neural modalities, such as motor influence on auditory systems. And thinking about the future, there are several questions left in mind, at least as far as I'm concerned. For once, although we saw the enhanced neural representation of melodies by tapping, we don't know how exactly it is translated to the subjective experience of the participants. Does tapping improve the accuracy of imagined music from a behavioral perspective? There are certain findings that hints that might be the case. For example, there are evidence that tapping improves auditory perception, and also tapping could improve anomic representation of music in different ways. We did try to identify such an effect in extended behavioral test of imagery accuracy, which was performed before the scan, as I briefly described earlier. So I won't go now into the details of the test unless you're curious, but the bottom line is that participants' accuracy of imagery did not improve when they were tapping while imagining the melodies. And it's obviously hard to interpret these null results, and measuring the accuracy of imagery is an extremely tricky task. So I believe there's still a lot of work to be done here. I'm also interested in exploring the effect of rhythmic movement on involuntary imagery. For example, would tapping increase the likelihood of musical content to appear in our mind's ear like an earworm? And another point is that although we did not observe content-specific representation outside of the auditory cortices, the lack of similar temporal responses across perception and imagery does not imply that imagined content was not represented there, but that this pattern of activation perhaps was not consistently locked in time to the perceived content. It's possible that some additional regions do not replay the melodies in the rhythm they were originally perceived and imagined, but instead reinstated them in a temporally compressed or even reversed fashion, as has been previously demonstrated during retrieval of visual sequences. And finally, here we studied auditory imagery in a form that is likely to be expressed in a relatively very sensory level of experience. In other words, the imagery of music must involve recalling sensory features such as pitch and tempo and timbre and so on, but other forms of common complex auditory content such as spoken language could potentially rely more heavily on the abstract semantic content, and therefore might not involve such a strong sensory component as in music. So it could be interesting to study how imagery could occur in different levels of abstraction. So that's it for now. I want to thank all my collaborators, starting with Robert Zatorre, my advisor from the MNI, and also Andrea Halpern, Annie Patar, and Adrian Owen, and to all our finding agencies, of course. And thank you all for listening. And that's it for now.
Thank you very much, Moore. We should have, you know, like recorded applause like they do in TV shows. That
Yeah.
we could set that up now.
Mm.
So it's great. I don't know what our timing is. It's 4:30, so I think we have time for a few questions. People are encouraged to write them in the chat. And I don't see any yet, but I was going to ask you, oh, well, here's one. Here's a question. It says, given that participants learned the melodies by humming, was there any notable replay in motor areas associated with voice or singing?
Right, that's a good question.
Yeah.
So you would expect that during, even if they're just internally imagine the experience, maybe their practicing of this motor humming will be associated in once they imagine the auditory information in a way, they also imagine the motor sequence of humming. So I definitely, it's something I would think we might have been, we could see, but I admittedly I'll say we didn't. And I explored it quite a bit in the data, but we didn't see any motor activation that is unique for the pattern, right? So I just want to emphasize, we're not talking about general activation. It's not like the motor regions were not active on average of the pulse signal, right? If we're talking about the temporal pattern specifically that was locked in a similar way across people, that was not present. But the general activation might have been there, definitely. So it might be, we might be able to interpret it that maybe the motor experience maybe is not as synchronized across people or similar across people as the auditory experience. I'm not sure actually, but it's very interesting.
We've talked about this before, and in many previous studies, the supplementary motor area is often active during musical imagery. And that's always been interpreted, you know, as some kind of motoric response. But as you point out, this particular technique is sensitive to the temporal synchrony of the signal. And I think what's relevant there is that it also is about the sort of precision of the representation, right? So maybe the humming or any vocalization may not have the same precision to it, because it may just may serve a kind of an adjunct function, you know.
Right. You can think about,
Sorry, the other point is that in the instructions to the participants, did you ever tell them, you know, not to hum, or did you?
Oh, definitely.
Yeah.
We of course asked them not to hum actively. We also had a mic in the scanner with an experimenter constantly listening to make sure they're not actually moving their lips or vocalizing anything,
Right.
which was important. But yeah, it's important what you said, Robert, as you mentioned. I mean, we specifically in this type of analysis look at dynamics over time, right? There could be an activation. It's important to emphasize it. And an activation that is relatively stable over time, maybe more of a control mechanism that motor regions are involved in. But because when there's no variance over time that follows the stimuli or the task that is synchronized across people, then this is a case we won't be seeing synchronization like that.
Yeah. Good. Okay, here's another question. Is there any way to disentangle the temporal and pitch components of the replay in the neural correlations?
Well, theoretically, people can do, we don't have enough data in this case, but you can theoretically look for certain correlation between pitch and when you see correlation over time. So for example, if there are certain parts of the melody where there is a higher pitch or a different maybe melodic structure, and other places the pitch changes over time. But the point is that we're not tracing a specific pitch or specific temporal structure that is in a single point in time, because we need that fluctuations over time to look for the pattern. So we could look maybe on certain general harmonic structure that changes over time, not a specific pitch, or certain changes in tempo over time. And then maybe we can kind of try to disentangle certain features that change over time. But we can actually, using this method, find a specific point in time and say, well, this was that note or this note and so on.
Well, you could, so for instance, people have done this, of course, you could take the stimulus and extract all of the onsets and create a regressor, which consists of just the onsets and the durations, for instance, which would be perhaps a way of modeling only the temporal component without any pitches. So if you applied that and looked for the correlation between brain activity and that input signal, what would you find?
Right. That's true. You can do regression analysis, basically. You can do it for the envelope of the sound and many different things, definitely. In this case, I don't know, I mean, I did actually a regression of the envelope, for example, to make sure that the early auditory regions are indeed in correlation with the envelope and so on, as people notice that oftenly we see in primary regions. But yeah, the question is what kind of unique information we would find in this case about imagery.
Yeah, it might not tell you about imagery, but I guess it would be a way of looking specifically only at the temporal component. So, so to the extent that you could show that, you know, the correlation with the amplitude envelope only occurs in certain regions, you could at least say, well, those regions are sensitive to that temporal feature.
Although you can't dissociate it from the actual different pitches in this case.
I'm trying to think of a way to do that, and I can't think of any.
Well, in a new set of data, maybe in percussions or something like that.
Yeah, so the follow-up question says, doing the analysis that Robert proposed, would you expect these same auditory areas, or are they unique to the pitch contour?
The temporal, I assume the temporal, as when thinking only about a tempo. That's a good question, but I do think that even relatively early or associative auditory regions will react to the tempo, even if it's the same pitch. So definitely, if this is what you're referring to.
Yeah, I guess in a different experiment, you could imagine having, you know, the same order of pitches with different durations versus the same durations with different orders of pitches. And maybe you could somehow model the temporal structure versus the pitch structure. I mean,
yeah.
I'd have to think about it. But...
Yeah, me too. Definitely.
But those are good questions. I mean,
yeah, but there are different ways to experiment with the different features and try to disentangle things. But the important thing is you need to get used to the idea of working with long naturalistic stimuli as music and language, which is by definition not as a control environment as a lot of scientists are used to in cognitive neuroscience, right? We are not isolating the tiniest pitch or frequency and so on. This is a messy environment by definition. So I like to look at it as a big fluctuating unit with dynamics and so on, rather than picking at the local effects.
Yeah, and there's a case to be made that for music that the pitch and the temporal dimensions are actually integrated, right, in their cognitive representation.
So what I would say is, what is, I mean, of course, there's a representation of a pitch, a specific pitch, but a pitch, I think, within the context of music, in each point in time, the same pitch might get a different context, and therefore could look or be represented in a completely different way based on where it is in the melody. And this is what I find most.
Yeah, well-known phenomenon in music cognition, obviously, that if a note appears, you know, as the leading tone or as the dominant, it's a very different function.
Exactly.
So there's another question. How was the choice of music made, specifically Joe Hisashi's music?
Obviously, there's always a subjective point of view a bit with our own preference for stimuli. But I would say this, I was looking for melodies that will last for about a minute at least. They'll be complex in terms of instruments and things going on, dynamics, not a boring melody that was obviously designed in a lab, but very naturalistic and engaging experience. On the other hand, of course, I didn't want any lyrics, but because then we are getting another level of semantics and so on that could interfere with our results in a very interesting way, but we didn't want it in this experience. But as I said, the other idea was trying to find a melody that will be relatively simple and catchy, because we did want subjects, which are random students in the university, to be able to hum it very easily. So melodies from these animation music were designed to be fun, create experience, right? You don't want it to be boring, it adds to the experience of the movie. On the other way, they're not very complex. They're not taking your attention away from something important. They're catchy. They stick in your head. And we did see it, that people actually continue and hum it for a long time after the experiment ended. So I think that was a useful, and I think it's a cute, the melodies are kind of cute, but we can argue about it. We do argue about it.
Yeah, they're not my favorite, but I think they do the job. And also you needed 6 of them that were somewhat comparable in duration and style and
the rhythm, of course, should be as stable as possible. We can't have something enthusiastic that changed the dynamics and the tempo over time. We want a stable tempo, so it also plays into the choicing of the.
Okay. I'm waiting to see if there are more questions. Here's one. So another follow-up to the contour timing question: would low temporal resolution bias the analysis towards longer contour-specific effects? In other words, the low temporal resolution of the bold signal, I think, is what the question refers to.
So whether low resolution, basically lower resolution of signal sampling would create
the fact that bold is necessarily slow.
Yeah.
Would it bias the analysis towards longer contour-specific effects, or it doesn't have to be contour, but I guess longer effects that occur over that time range? as opposed to effects that were occurring on a much
Well,
faster.
definitely dealing with fMRI, we're not looking at very accurate temporal effects, right? We're not looking at what we see, the kind of signal we see in EEG and MEG. We're looking for longer effects. Even though it's temporal, it's still summation of a few good seconds, right?
Yeah.
But I would say that those melodies we used are only 4 minutes, which is not a long time to use for this analysis. And there certainly could be certain phenomena as experience of music that needs more time, right? Maybe we need like an integration of more musical context and experience and so on that lasts for 2 minutes or 4 minutes and so on. So you have longer musical experience and it will involve more regions of the brain in processing this maybe richer, maybe more complex experience.
Right. But that's sort of the other side of the question. But I think the question was about what happens if you have very quickly changing events that people are imagining. I guess we're not sensitive to those.
Right. If it's, we definitely cannot track the milliseconds, as I said. We are looking at slower fluctuations over.
But we could, and I think we've discussed it at some point, that we could do the same experiment with MEG, for example.
For sure. So people have been performing the analysis, right? At least the intersubject analysis.
Yeah.
That was performed using both EEG and MEG and so on. So definitely you can use this kind of modeling, you would say, of this kind of shared responses over time, and then you'll get more resolution, temporal resolution, obviously.
Right. And would you expect that the results would be terribly different if you were able to track the intersubject correlation of rapidly changing events?
The only way I think we might be able to see different, I think results might be in early auditory regions where they really track nuances. If the music is very rapid and so on, we're talking about those kind of.
But we already saw. We already did see responses in those.
We did, but maybe we'd see more. For example, maybe we'll see effect of tapping now also in early auditory cortex in certain nuances we were not able to capture in this case. But overall, we're looking on much slower effects that related to the conscious experience, I think, of the music specifically. There were studies before using the same method and trying to scramble spoken language in different levels, for example, words, sentences, paragraphs, and so on, and reverse. And you see the entire hierarchy along the superior temporal gyrus, but we see from early auditory cortexes to frontal regions and so on and so forth. So definitely there's some information that we just can't capture in EEG and MEG, some temporal resolution. But in terms of the components of music that you can experience in music and the association with those specific components that are a bit slower, I don't think that would add more, but maybe certain neural effects that are faster, right? In high resolutions.
Yeah. Sure, and I guess it depends on the speed of the events occurring within the music, right? Maybe depending on the style of music or so forth. If it has very fast changing things, or you have, I don't know what, arpeggios or something that occur very rapidly, or ornaments or things like that.
Right.
As opposed to, I think most of these melodies themselves are kind of on the slowish side.
Yeah, they're pretty calm. I mean, some are a bit more, but yeah, they're pretty calm. But even very fast melodies, I don't know if a fast arpeggio would be captured better in EEG than just an average signal.
Yeah,
in a good enough sample of bold signal.
Right. Well, and there are cognitive experiments showing the range over which, say, a melody is recognizable.
Right.
And Andrea would know about this, for instance, but if you make it too fast, even though you can perceive the sounds, they no longer sound like a melody. You can't hold on to it. And similarly, if it's too slow, if you drag it out too long, then it also falls apart because your working memory capacity doesn't hold on to the sounds so that you can relate the different elements to each other. So, and if you look at the music of all different cultures around the planet, they all conform to those boundaries.
Right.
So
maybe low, as you say, like maybe lower level effect, neural effect, but things that are directly associated with the more natural way we listen to music. I'm not sure.
Yeah. This is also related to the theory of sensory motor coupling,
Mm-hmm.
whereby, of course, for speech, we know this is an old idea, but for music, it's a more recent idea that, you know, the temporal relationships are also limited by the effectors. And so, you know, you can only move your lips and your tongue or your fingers with a certain speed,
Right.
and you can't move them any faster. And it's not that surprising that both music and speech use, you know, temporal events that are in the, you know, sort of a 2 to 4 hertz range, the most prominently, because that's the way that it's easiest to articulate or to move your fingers.
Right.
Good. Well, I don't see any more questions. I'd be happy to address them, but probably we should let people go. If there are any more questions that you think of later, of course, you can address them directly to Moore via email. So thank you, Moore, for the talk, and thank you, all of you, for participating, and hope we will see you again next week at next week's Feindel Virtual Brain and Mind Symposium.
Thank you very much. Bye.
Bye-bye.